Welcome to Spelling Bee Ninja. In today's episode, we'll dive into the fascinating world of gravity and motion. Have you ever wondered what keeps the planets in orbit or why things fall to the ground? Well, you're in for a treat. We'll explore these concepts and more, unraveling the mysteries of how gravity works and how it affects everything around us. So, get ready to take a journey through space and time as we discover the forces that shape our physical world. Let's start with gravity itself. Gravity is a fundamental force that pulls objects toward one another. This force is proportional to the mass of the objects involved. The more mass an object has, the stronger its gravitational pull. Earth's gravity, for example, pulls everything toward its center, explaining why when you drop something, it falls down instead of up. Without gravity, the moon would drift away from Earth, and Earth would not hold its place in orbit around the sun. Understanding gravity is crucial, as it also leads us to history's great minds, like Isaac Newton. Newton is credited with being the first to describe gravity mathematically, and his journey into the world of physics famously began with an apple falling from a tree. This simple observation led to groundbreaking principles that define how we understand motion today. Now, let's consider mass and weight. Mass refers to the amount of matter in an object and is measured in kilograms, while weight is the force of gravity acting on that mass and is measured in newtons. It's interesting to note that your mass is constant, no matter where you are in the universe, but your weight can change depending on the gravitational pull of the celestial body you're on. For example, if you were on the moon, which has only 1/6 of Earth's gravity, you would weigh significantly less, but your mass would remain unchanged. Imagine how exciting that would be. Your body would feel so much lighter. Next up, let's discuss Galileo Galilei, a key figure in the history of physics. Back in the 16th century, Galileo dropped two balls of different masses from the Leaning Tower of Pisa to show that they fall at the same rate when ignoring air resistance. Before him, many believed that heavier objects fall faster than lighter ones, a misconception dating back to Aristotle. Galileo's findings paved the way for the understanding that all objects, regardless of their mass, accelerate toward Earth at the same rate due to gravity. Isn't that remarkable? Now, when you drop a heavy ball and a light ball from the same height without air resistance, both will hit the ground simultaneously. Moving forward, let's take a step into Newton's first law of motion, often referred to as the law of inertia. This law states that an object at rest remains at rest, and an object in motion continues to move at the same speed and in the same direction until an unbalanced force acts on it. This principle is fascinating because it indicates that in the vacuum of space, where there is no friction or air resistance, a spacecraft can coast indefinitely without using fuel. So, what keeps a moving object in motion? It's the absence of force acting against it that allows it to persist in its current state. As we delve deeper, we encounter Newton's second law of motion, articulated in the equation force equals mass times acceleration, or F equals ma. This law explains that if you increase the mass of an object, more force is required to accelerate it. Conversely, if you apply the same force to two different masses, the lighter object will accelerate more than the heavier one. Think about kicking a soccer ball versus a bowling ball. The lighter soccer ball moves quickly with a soft kick, while a bowling ball requires much more effort to achieve the same acceleration. Now, let's not forget Newton's third law of motion, which tells us that for every action, there is an equal and opposite reaction. This means that forces always come in pairs. For instance, if you push against a wall, the wall pushes back with equal force, preventing you from going through it. A perfect example of this is a rocket launching into space. As the rocket's engine expels hot gases downward, there is an equal and opposite reaction, propelling the rocket upward. It's a delicate balance that allows for incredible feats of engineering. Next, we need to talk about friction. Friction is the force that opposes motion between two surfaces in contact. It's a critical aspect of our everyday lives, making it possible to walk without slipping and eventually bringing a moving ball to a stop. There are two main types of friction: static friction, which prevents objects from starting to move, and kinetic friction, which resists motion when objects are already sliding. For instance, static friction is what keeps a parked car from rolling down a hill. Without this force, the car would not remain in place. Now, let's explore the concept of orbits, which is particularly captivating. An orbit occurs when an object is falling toward a larger body but has enough sideways velocity to keep missing it. Take the moon, for example. It's constantly falling toward Earth, but its forward motion keeps it in a stable orbit. If the moon moved slower, it would eventually crash into Earth, while a faster speed would cause it to escape Earth's gravitational pull. This same principle applies to satellites that orbit our planet, making it a fundamental concept in both astronomy and physics. Speaking of gravity, did you know that near Earth's surface, all objects accelerate downward at approximately 9.8 meters per second squared, regardless of their mass? This means that for every second an object falls, its downward speed increases by 9.8 meters per second. After just 1 second, the speed would be nearly 9.8 meters per second. After 2 seconds, it would be about 19.6 meters per second, and so on. However, in real life, air resistance does limit the speed of falling objects, leading to a phenomenon known as terminal velocity. This is particularly relevant when we think about skydivers, who reach a terminal velocity of around 120 miles per hour before they open their parachutes. Finally, we can't discuss gravity without mentioning Einstein's theory of general relativity. Introduced in 1915, this revolutionary theory redefined gravity not as a force, but as the curvature of spacetime caused by mass and energy. In this framework, massive objects like the Sun warp the fabric of spacetime, causing smaller objects such as planets to follow paths along that curvature. This concept also explained certain behaviors of Mercury's orbit, which Newton's laws could not clarify. Furthermore, Einstein predicted fascinating effects such as gravitational lensing, where light bends around massive objects, and time dilation, whereby time runs slower in stronger gravitational fields. This perspective on gravity provides a profound understanding of how the universe functions. Today, we've embarked on an enlightening journey through the realms of gravity and motion. We started with the fundamental nature of gravity, discussed the principles of mass and weight, and explored the significant contributions of historical figures like Galileo and Newton. We also dissected Newton's 3 laws of motion and considered the role of friction and orbits. Finally, we dove into Einstein's groundbreaking theory of general relativity, which gives us an entirely new way to think about gravity. These concepts are not only fundamental to physics but also crucial to understanding the universe around us. Thank you for joining us today on this exciting exploration of gravity and motion. We hope you've gained new insights into the forces that influence our lives and the world we inhabit. Keep your curiosity alive and continue discovering the wonders of science. Until next time, stay curious and keep exploring.